Okay, continuing to work on Unit 10, Set 3. This video is going to just work through some of the exercises in that set. And I know that there's a lot of material in Set 3, and it's probably very difficult to do this, especially at a distance. So I thought it might be helpful to work through some of the problems. All right, so let's start with number 1. And let's do problem B, where we have the number negative 3i, and we're asked to find the modulus. Okay, and there's a couple of ways to go about finding the modulus here. The most obvious thing is to just simply ask yourself, where is the number minus 3i? And of course, minus 3i is at this point right here on the vertical axis, right? Remember, we label the vertical axis with values of I. And so negative 3i sits at the same point as the Cartesian point, 0, negative 3. And the modulus is how far the point that represents that number is from the origin. So obviously that is 3 units away. And the symbol for modulus is just to put absolute value bars around the number. And so we can say that the modulus of minus 3i, or just say the absolute value of minus 3i, is 3, because that number is 3 units from the origin. Now, another way to look at that is to say that negative 3i, if you put it in strictly a plus bi form, right, a plus bi form, that would be 0 minus 3i, and we can use that formula that we talked about in the earlier video, that the modulus, or the absolute value of a plus bi, is the square root of a squared plus b squared. So in the case of minus 3i, we can say that the modulus is the square root of 0 squared, because 0 is the value for a there, plus negative 3 squared. Negative 3 is the value for b. And that gives us 0 squared plus negative 3 squared is 0 plus positive 9, right? When you square a negative, you get a positive. So that's the square root of 9, which is 3. So same answer either way. But that's just 2 different ways of looking at how to get the modulus of that number. All right, let's look at number 1F, where we're given the number 3 minus 4i. All right, so we could draw a picture of this. Let's see, this is going to correspond to the Cartesian ordered pair 3, negative 4. So we go 3 units to the right and 4 units down. And the modulus, of course, is how far is this point right here. This point is the point 3, negative 4, and that's the point in the plane that represents this number, 3 minus 4i. And so this distance here on this hypotenuse is the modulus of that number. Now, you might recognize this as our old friend, the 3, 4, 5 right triangle. And if you do, then right away you know that the answer is 5. Or you might appeal to that formula again. If you like formulas, you want to always do things the same way and use the formula, then that's fine. So this will, the modulus of this will be the square root of 3 squared, since 3 is the value of a, plus negative 4 squared, because negative 4 is the value of b. So that's the square root of 9 plus 16. 9 and 16 makes 25, and the square root of 25 is 5. All right, so a couple of ways that you could come up with that modulus. You could know your 3, 4, 5 special right triangle, or again, you can just plug into the formula for the modulus, or the absolute value of the number. All right, so let's try some problems in number 2. In number 2, we are looking for the argument of the number, which means we want to know on the terminal side of what angle does the point representing the number lie. So in number 2, we're looking at the number 5i. So let's plot. Where does 5i go? Well, all of those multiples of I go on the y-axis, right? This is 1i, 2i, 3i, 4i. Here's 5i right there. And it lies on the terminal side of the angle pi over 2, right? So there we go. The argument of 5i is pi over 2, because when you plot that number in the number plane, it lies on the terminal side of pi over 2. Okay. Let's look at one that is not on an axis. How about number 2, f, the number 1/2 minus root 3 over 2i. Right, so let's plot that one. Let's see, we're going to go 1/2 to the right and root 3 over 2 down. So that number lies right there. And we get this triangle. And when we see these side lengths here, we see we've got 1/2 of 1 and 1/2 of root 3. And 1 and root 3 remind me of my 30, 60, 90, right? If I start with a 2, 2, 2 equilateral, all the angles in there are pi over 3, right? And when you split it down the middle, that's 90, that's 60, so this is 30, or pi over 6 radians. And we split this side down here in half, so that's 1, and then 4 minus 1 is 3, so that side's root 3. So there's kind of our standard 30, 60, 90. And if you divide all of these sides by 2, if you make all of them half as long as usual, then the hypotenuse is 1, the short leg's 1/2, and the leg across from pi over 3 is root 3 over 2. And that's what we've got here, right? We've got a leg of 1/2, and the other leg is root 3 over 2. So this hypotenuse is 1, and this angle is the angle opposite from pi over 3. Opposite root 3 over 2. And so if this reference angle here is pi over 3, then the angle that has its terminal side going through this point that we're interested in is 5 pi over 3, right? A whole rotation of 6 pi over 3, and we back it up by 1 pi over 3 to get back to 5 pi over 3. Okay, so the argument of this number is 5 pi over 3. So it's still a matter of knowing your special triangles. If we were doing this in class and we had more time and we could sit down with calculators, we would look at some examples that did not depend on knowing the special right triangles, but we just don't have the setup to do that right now. All right, let's look at some problems in number 3, where we're trying to simplify. Let's try letter E. All right, so this is one of those problems where we're doing what I call basic algebra. We're going to be using the distributive property, and we're going to be collecting like terms. Okay, so we need to distribute the root 3 through the first set of parentheses here, and then after that we'll need to collect the like terms. So root 3 times 1 over root 3, well, the root 3 on the bottom and the root 3 on top cancel out, leave you with 1. And then root 3 times root 3 is 3, so that's 3i. And we've got a negative 1 here and a negative 3i. So when we collect like terms, what happens? The 1 and the negative 1 are like terms, and the two terms that have I in them are like terms. And we see that everything, that both these pairs of like terms are opposites, right? So 1 and negative 1 adds up to 0. 3i and negative 3i adds up to 0. So we get 0 when we simplify this expression. So nothing here that's really even depends on knowing what I means. You can just think about I as being a variable here, and then this is just a problem about distributing and collecting like terms like you would have in Algebra 1. Let's try one of those that you wouldn't have in Algebra 1, like H. All right, so that's where we're trying to add 2 cis pi over 6 to 4 cis 5 pi over 6. All right, and the only way to add these is to just convert both of these back into Cartesian form, that is a plus bi form. All right, there just isn't a good rule for adding numbers that are in modulus argument form to each other. So this number here represents 2 times cis pi over 6. And cis pi over 6 is just an abbreviation for the cosine of pi over 6 plus I times the sine of pi over 6. Right? And then 4 cis 5 pi over 6 is an abbreviation for 4 times the cosine of 5 pi over 6 plus I times the sine of 5 pi over 6. So all I've done here is just expand these expressions by replacing the cis expressions with what they stand for in terms of sine and cosine. All right, so now let's evaluate all this. The cosine of pi over 6 is root 3 over 2, and the sine of pi over 6 is a half, and the cosine of 5 pi over 6 is negative root 3 over 2, and the sine of 5 pi over 6 is positive 1/2. All right, and now let's do the distributive property. So we got 2 times root 3 over 2 is root 3, and 2 times a half is 1, so that's 1i. And then over here we got 4 times negative root 3 over 2, so that's going to be negative, right? 2 goes into 4 2 times, so that's 2 root 3, and 4 times a half is 2 times I. Right, so that's just doing the distributive property. And now we will collect the like terms. So we've got a root 3 and minus 2 root 3 makes minus 1 root 3. And we have a positive 1i and a positive 2i makes 3i. So there is our answer in a plus bi form, or Cartesian form. All right, let's move on and look at a couple of problems in number 4. And what we're doing here is just good old-fashioned FOIL, right? So we're going to multiply the first terms together, and then the outer terms, the inner terms, and the last terms. Okay? So for the first terms, we'll get root 2 times 1 over root 2. Well, the root 2 on top, root 2 on the bottom cancel out and just leave us with 1. Okay. Now, how about the outer terms? Well, again, the root 2 times the 1 over root 2, those square roots cancel out and just leave us with minus 1i. And from the inner terms, root 2 times 1 over root 2, that cancels out, and again we get a minus 1i. And finally, from the last terms, the root 2 and the 1 over root 2 cancel each other out, The two negatives cancel each other out, and we still have an I times an I makes I squared. Alright, so that part was just straightforward, doing FOIL. You don't even have to know what the I means to carry that out. Now, you do need to know what I means in the next step, because we're going to replace I squared with -1. All right, remember that is what I does. I is the square root of -1, so its square is -1. So we should never leave I squared in an answer, because I squared is just -1. So we get 1 plus -1, well, that adds up to 0, and then we've got the two i's there that add up to minus 2i. And let's try 4D. 4D, we've got the square root of 3 minus I squared. But to square something means to multiply together two factors of it. So that's just going to be FOIL again, right? We're going to multiply this root 3 minus I times itself. So from the first terms, we get root 3 times root 3 is 3. And then we get minus root 3i from the outer terms and minus root 3i from the inner terms. So that's two of those, right? Minus 2 root 3i. And finally, from the last terms, a negative times a negative makes a positive, and an I times an I makes an I squared. But remember, I squared is really -1. So we've got, for like terms here, we've got 3 and minus 1, that makes 2. And then we've got the minus 2 root 3i. So there is our answer in A plus BI form. Okay, if we take a look at a problem number 5, let's do B. We have to multiply cis pi over 3 times cis pi over 6. All right, so this is using one of the parts of de Moivre's formula, or de Moivre's theorem. And one part of that said that if you multiply R cis alpha times S cis beta, that you're going to get R times S times cis alpha plus beta. Right? So we've got a rule for how to multiply complex numbers when they're in modulus argument form. There is no rule about adding them. So that's why up here, when we were going to add those numbers in modulus argument form, we just had to rewrite them in Cartesian form and then add the like terms. But when it comes to multiplying, you don't have to convert to a Cartesian form, because we've got de Moivre's theorem that tells us how to carry out this multiplication. In these problems, of course, the modulus for both of these is 1, so we just don't have to bother worrying about the modulus, because 1 times 1 is 1. So all we need to worry about is the fact that we're supposed to add the two arguments. So this is going to be cis pi over 3 plus pi over 6. All right, so when we multiply numbers that are in modulus argument form, we always add their arguments. So let's see, that's 2 pi over 6 plus 1 pi over 6 makes 3 pi over 6, which of course is pi over 2. Right, so this is the modulus argument answer there. And it says give it in both forms, right? Give the modulus argument form of the answer. So that's one way to answer this question. But it also says to give the A plus BI form. And so to do that, we'll just convert this by writing out what does cis pi over 2 mean. it means the cosine of pi over 2 plus I times the sine of pi over 2. Remember, this is really just shorthand for this longer expression here. And the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. So this is 0 plus 1I, or just simply I. All right. By the way, instead of expanding that and coming up with I that way, you could have just said to yourself, well, cis pi over 2, it's got a modulus of 1, so it is the number that is 1 unit away from the origin in the pi over 2 direction. In other words, straight up. And that, of course, is exactly where I lives, right? 1 unit above 0. All right, let's try another one in number 5. Let's do F, where we're multiplying 5 cis pi over 3 and 2 cis pi over 3. So this time we are going to have to worry about the modulus numbers, the moduli. And what does Demoivre say about that? Well, he says that you just multiply those modulus values together. So when we multiply these two numbers together, the new modulus, the modulus of the product, is going to be 5 times 2 makes 10. And what do we do with these arguments? These angles here, when we multiply, we add them. All right, so the product of these two numbers is 10 cis 2 pi over 3. Right, so there is one form of my answer. That's the modulus argument form of the answer here for this product. And we're being asked to also give the a plus bi form, so let's expand this out. This is 10 times the cosine of 2 pi over 3 plus I times the sine of 2 pi over 3. All right, so let's evaluate those trig values. 2 pi over 3 is in the second quadrant, where cosine is negative, and sine of 2 pi over 3 is positive. We're in the second quadrant, and the sine of 2 pi over 3 is root 3 over 2. And if we distribute the 10 times negative a half is negative 5, and 10 times root 3 over 2, the 2 goes into the 10 5 times, and so we're left with 5 root 3I. So here's the Cartesian form, or the a plus bi form of that answer. So these two answers are the same thing. It's just that they're different ways of expressing that complex number. Okay, in number 6, let's try letter A. And we're asked here to use Demoivre's theorem to raise these complex numbers to powers. You could, of course, if you really were determined to, you could raise this to the 4th power by squaring it, multiplying it by itself with FOIL, and then take that answer and square that answer, because the square of the square would give you the 4th power. But we're trying to do this using Demoivre's theorem. And what does Demoivre say about raising a number to a power? Well, we're told that if you have r cis theta and you raise it to the nth power, that you raise the modulus to the power and you multiply the argument by the power. All right? So that's what Demoivre says. So that means that to use Demoivre in this problem, we've got to take this number here, 1 over root 2 minus 1 over root 2i, and we've got to rewrite it in modulus argument form, because we need it in that form if we're going to apply Demoivre's theorem. So let's plot this number, 1 over root 2 minus 1 over root 2i. So let's see, we're going to go 1 over root 2 to the right, and 1 over root 2 down to get to that number. And this is obviously a 45, 45, 90 triangle, right? Because the two legs are equal, so that means these two angles have to be equal. So they're both pi over 4 radians. And what about the length of this hypotenuse? Well, you could use the Pythagorean theorem here. If you square 1 over root 2, you get 1/2, and 1/2 plus 1/2 adds up to 1. And the square root of 1 is 1. Or you could just recognize this is our typical 45, 45, 90 triangle, but all the sides have been divided by root 2. Right, so the legs are 1 over root 2, and if you divide the hypotenuse by root 2, you get 1. So you can get that hypotenuse length either way. And if this angle's pi over 4, then this angle here with the positive x-axis is 7 pi over 4. Right, pi over 4 short of a whole rotation. 8 pi over 4 is a whole rotation. So this number right here can be written. So now that we've got the modulus argument form for this number right here, we can rewrite this as the modulus, modulus is 1, and the argument is 7 pi over 4, and we're raising this to the 4th power. All right, so following de Moivre's theorem here, we raise the modulus to the power, but 1 raised to any power is just 1, so we don't have to do anything with that. And then we multiply the argument by the power. So this becomes cis 4 times 7 pi over 4. Okay, the 4 there is this exponent, so the exponent gets multiplied times the argument, the angle. And of course those 4's cancel, and that gives us cis 7 pi. And that's really an okay answer here, except 7 pi is more than a whole rotation. So let's see if we can find an angle coterminal with 7 pi that's not quite so big. So let's see if we go all the way around one rotation, that's 2 pi. 2 rotations is 4 pi. 3 rotations is 6 pi. And so for 7 pi, we need one more pi, which is one more straight angle. So here is 7 pi. 7 pi is 3 full rotations and one more half angle. So it is coterminal with pi. So the sine of the cosine of 7 pi will be the same thing as the sine of the cosine of pi. So here is our modulus argument answer. It's 1 cis pi, but we might want to go ahead and give that answer in Cartesian form or a plus bi form. So what does cis pi stand for? It stands for the cosine of pi plus I times the sine of pi. And let's see, the cosine of pi is -1, and the sine of pi is 0, so we get -1 plus 0i. And by the way, instead of writing out what cis pi stands for, we could have just said 1 cis pi is the number that's got a modulus of 1 and is has modulus of 1 and is on the terminal side of the angle pi. Well, what number is that? If you go 1 unit to the left in the pi direction, that number is, of course, -1. That's where -1 is on the real number line. All right, so there we have raised 1 over root 2 minus 1 over root 2i to the 4th power. Turns out it's -1. And just as a little observation here, that means that this number, the number in parentheses here, is one of the 4th roots of -1. Right? Because when you raise that number to the 4th power, you get -1. So this number in the parentheses here must be one of the 4th roots of -1. All right, let's try one more there in number 6. Let's do number 6F. We are raising -1 minus I to the 5th power. Okay, and so we know that we need to rewrite this number in here in modulus argument form. So let's plot it. Let's see, we're going to go -1 to the off to the left and -1 down, because this number, -1 minus I, corresponds to the Cartesian ordered pair, right? -1, -1. And look at that. That's a 45, 45, 90, isn't it? 1, 1, root 2, and that angle, that reference angle is pi/4. So this point here lies on the terminal side of 5pi/4. Right? That's the angle that this hypotenuse forms with the positive x-axis. So -1 minus 1i is root 2 cis 5pi/4. Okay, so we rewrote this number in modulus argument form by drawing the triangle. And now we're going to apply de Moivre's theorem. How do you raise a number in modulus argument form to a power? Well, you raise the modulus to the power, so we're going to raise root 2 to the 5th power, and we multiply the argument by the power. So we're going to multiply 5pi/4 times 5. Right, so the exponent got multiplied times the angle, and we raised the modulus to that exponent. Okay, so let's see. Root 2 to the 5th power, when I see that in my head, I see 5 factors of root 2, and I know that root 2 times root 2 is 2, and another root 2 times 2 is 2, and we've still got a root 2 left, so that's 2 times 2 makes 4 root 2. So root 2 to the 5th power is 4 root 2. And what's this angle? 5 times 5pi/4. Better work on that angle a little bit. That's 25pi/4. And let's see if we can find something that's coterminal with. If we make a whole rotation, that's 8pi/4. And another whole rotation will be 16pi/4. And so if we make a third whole rotation, that's 24pi/4. So how much is left? Well, just one more pi/4, right? So 25pi/4 is 3 whole rotations and one more pi/4. So this angle is coterminal with pi/4. And I'd much rather work with pi/4 than 25pi/4. All right, so here is our modulus argument answer. That's what we get when we raise -1 minus I to the 5th power. All right, now what if we want to give that in the Cartesian form? Well, let's rewrite cis pi/4 in sort of an expanded form, right? That's the cosine of pi/4 plus I times the sine of pi/4. That's what cis stands for, right? And let's see how much we got there. Cosine of pi/4 is 1 over root 2. And the sine of pi/4 is 1 over root 2. And so when we distribute there, 4 root 2 times 1 over root 2, the root 2's cancel and just leave us with 4. And same thing happens when we distribute it over here to this coefficient of I. The root 2's cancel and just leave us with a 4 and that I. So there is the Cartesian, or a plus bi form of the answer to the question, what do you get when you raise -1 minus I to the 5th power? All right, let's look at some of the root problems. Let's take a look at number 6b, where we're trying to find the 3 cube roots of -1. Okay, and just a reminder, every complex number except 0 has 2 square roots, 3 cube roots, 4 fourth roots, and so on. And so to get the cube root of -1, that means we're raising -1 to the 1/3 power. All right, let's rewrite -1 in modulus argument form. Just like up here, when we wanted to raise this number to the 5th power, we wrote it in modulus argument form so we could apply de Moivre's theorem. So we're going to do the same thing here with this fractional power. -1 is really easy to put in modulus argument form. -1 lives right here on the number line, 1 unit to the left of the origin. So its modulus is 1. It's 1 unit from the origin, and it lies on the terminal side of the straight angle pi. So -1 is simply cis pi. That's its modulus argument form. All right. And what does de Moivre say that we do? De Moivre says we raise the modulus to the power, but the modulus is 1. And 1 raised to anything is it's just 1. So what do we do with the argument here? We multiply by the power. So 1/3 of pi, that's pi over 3. So there's my modulus argument answer. The one of the cube roots of -1 is cis pi over 3. Okay, but let's go ahead and put that in Cartesian form. This is the cosine of pi over 3 plus I times the sine of pi over 3. And what's that? The cosine of pi over 3 is 1/2, and the sine of pi over 3 is √3 over 2. Okay. So there's one of the cube roots of -1. All right. Now, where do we get the other 2? It says there's 3 of them. Well, remember, when you're looking at the roots of a complex number, they're always equally spaced around a circle. So if you can find one of the roots, you can find the others by equally spacing, in this case, 3 points around the circle. Okay, so one answer is right here. This is on a circle with a radius of 1. This point here corresponds to the number 1 cis pi over 3, right? This angle's pi over 3. And if you've got 3 points to space around the circle, the whole circle has 2 pi radians. So if we chop that into 3 pieces, each point's going to be 2 pi over 3 radians from the other one. So if we're here at pi over 3, and we add 2 pi over 3, that gets us up to 3 pi over 3, which is just pi. So cis pi is another of the answers. And what's 3 pi over 3 plus another 2 pi over 3? Well, that's 5 pi over 3. So here is the third answer. By the way, if you add 2 pi over 3 to 5 pi over 3, you get 7 pi over 3, but that's just 6 pi over 3 plus 1 more pi over 3. So that's coterminal with this one. Okay, so all of these answers are 2 pi over 3 radians apart on the circle. Okay, they're equally spaced around the circle. So one of my cube roots of -1 is cis pi over 3. Another one is cis pi. Well, what is cis pi. Well, that is the point that's 1 unit away from the origin in the direction of pi. And of course, that is just -1 itself, isn't it? And we actually knew that number anyway, right? Didn't you already know that if you cube -1, you get -1? But it's kind of nice to see that that sort of natural answer crops up here in the procedure we're using. And then the third result was cis 5 pi over 3. Well, 5 pi over 3 has a reference angle of pi over 3. So the answer is going to look a lot like this first answer we got, except we have to think about what quadrant we're in. 5 pi over 3 is in the fourth quadrant, where the cosine is positive. So this value for A will still be a half. But in the fourth quadrant, the sine is negative. So the sine of 4 pi over 3 will be negative √3 over 2. So there is my third cube root. Okay, so we got 3 cube roots of -1. There's one of them. There's the one you probably knew in 5th grade. And there is the third one. Okay. All right, let's do one more of those. Why don't we do the 4 fourth roots of -16? So this is number 6F. We're looking for the 4 fourth roots of -16. All right, so that means we're raising -16 to the 1/4 power, right? The 1/4 power is the same thing as taking a fourth root. Let's rewrite -16 in modulus argument form. Well, -16 sits over here 16 units away from the origin along the terminal side of pi. So that is 16 times, didn't mean to say the cosine, that is 16 cis pi. And we're raising that to the 1/4 power. All right, so what does de Moivre say to do? Take the modulus and raise it to the power. Take the argument and multiply it by the power. So pi times the 4th is pi over 4. And what's the 4th root of 16? That's 2, isn't it? 2, 4, 8, 16. 2 to the 4th is 16. And so here is one of our answers, right? In modulus argument form, one of the 4th roots of -16 is 2 cis pi over 4. All right, and what is cis pi over 4? Well, it's the cosine of pi over 4 plus I times the sine of pi over 4. Now, usually, when I see the sine of pi over 4, I just think 1 over √2. But remember, sometimes when we worked with identities and things, it was more convenient to use the rationalized form, √2 over 2. And that's going to be true here because I'm going to be multiplying by 2. So if I write it so that there's a 2 in the denominator, those 2's will cancel out, won't they? So this is 2 times √2 over 2, which is just √2. And sine of pi over 4 is, of course, the same as the cosine of pi over 4. So 2 times √2 over 2 is √2. So there's one of the 4th roots of -16. √2 plus √2 times I. Now, where are the others? Well, the others are going to be equally spaced. I know that's a terrible circle, right? They're going to be equally spaced around the circle. And the circle is going to have a radius of 2, right? That's the modulus of this number. And so one of the answers is 2 cis pi over 4. What if we equally space 3 others? Well, if we equally space 3 others, then they're going to be at 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, so those are our roots. They're all 2 pi over 4 or pi over 2 radians apart. So here's one of our roots. Another one is 2 cis 3 pi over 4. Well, the reference angle for 3 pi over 4 is pi over 4. So the answer is going to look a lot like the first answer we got, except we know that the cosine in the second quadrant is negative and the sine is positive. And we get another answer in the third quadrant. Sorry, that's 4. So again, 5 pi over 4 has got a reference angle of pi over 4. So the answer is going to look a lot like the first one, except the sine and the cosine are both negative in the third quadrant. And finally, 2 cis 7 pi over 4 in the fourth quadrant. 7 pi over 4 is in the fourth quadrant. The cosine's positive, so that'll be positive root 2 for the cosine, but the sine is negative. So here are the 4 fourth roots of negative 16, right? There's 1, 2, 3, 4 of them. Notice that none of them are real. You didn't have an answer to that question in middle school. What's the fourth root of negative 16? Because they were all complex. You did have an answer to that last one, right? The cube roots of negative 1. You could have answered that question in middle school because when you cube negative 1, you get negative 1. So one of the answers there did turn out to be real. All right, so I hope going through those problems has helped move you along there on set 3.